one-dimensional kinematics topic. This section is 2.1, how do scalars differ from vectors? We'll be using distance versus displacement as an example of a scalar and a vector and how they're different. I'd like to start by saying that you will be learning about many physical quantities in your physics class, such as time, distance, acceleration, kinetic energy, work, charge. I'm just naming a few of the many scalars and vectors that you will be learning in physics. And they're going to fall into two very broad categories. They're either going to be scalars or they're going to be vectors. Now, I'd like to start with the definition of the word magnitude. All right, the word magnitude means just a number. Right? A magnitude is just a number, usually with an accompanying unit. For example, 4 meters is a magnitude. So you really don't have to worry too much about the word magnitude. If they ask you in a physics question to find the magnitude of whatever, they're asking you to calculate the number. Just get the answer. All right, so don't worry too much about the word magnitude. It really just means number with a unit, usually. Now, the word scalar. A scalar is a physical quantity that has only a magnitude, usually with a unit. A scalar has only a magnitude. So an example of a scalar quantity would be distance. And if I were to write, Jasmine walked a distance of 4 meters, there's the magnitude of the distance that Jasmine walked. And again, a scalar has only magnitude, so here we have only a magnitude and its accompanying unit. Now, a vector, on the other hand, has both a magnitude and so, if we were to use Jasmine as an example, then we could write Jasmine's displacement was 4 meters east. Remember that displacement is a vector, and a vector must have a magnitude. Here's the magnitude of Jasmine's displacement, and here is the direction of Jasmine's displacement. So the difference between the definition of a scalar and a vector, they both have magnitude, but the vector also must have a direction. All right. What I'd like to do now is give you an idea for a study skill to help you initially to memorize the scalars and vectors that you learn. Later on in the year, as you start using scalars and vectors, you will acquire more of an intuitive understanding as to which physical quantities are scalars and vectors. So you won't have to memorize them, you'll understand better. But for now, you are going to have to memorize a little bit which physical quantities or parameters you learn that are scalars and which are vectors. Here is the chart that I would suggest to help you to memorize this. Now, I'm only going to start the chart here. If you would like to see the entire chart of all the scalars and vectors that you learn in the course of the physics year, go to the Study Skills section of the website and look for the chart on scalars and vectors in the second section, One-Dimensional Kinematics, Study Skills. So, here's the chart. You would first kind of divide the page into two halves, left column, right column. You would put the scalars in the left column and the vectors in the right column. Each scalar that you learn is going to have the name of the quantity, the symbol of that quantity, and the unit, which again is going to be a symbol. Each vector that you learn will have the name of the quantity, the symbol of that quantity, and the unit, the symbol for the unit. So, here we go. The first scalar that I will mention to you is time. The quantity, the physical quantity, time. The symbol is lowercase t. Now, you cannot use a capital T for time. That's for period or maybe for temperature. In physics, uppercase and lowercase letters have specific meanings. If the symbol for time is a lowercase t, you cannot use an uppercase T for time. And the unit is the second, lowercase s. We're not going to put a corresponding quantity on the vector side for time. Time is going to stand alone. Now, the next scalar that I'd like you to memorize for now is distance. So we put distance on the scalar side. The symbol for distance is lowercase d. The unit for distance is the meter. Now, there is something unusual about distance and its corresponding vector, displacement. What's unusual is that they both have the same symbol and unit. This is not going to come up too often in physics. We like to have a specific symbol and unit for each quantity, but distance and displacement kind of share the symbol, lowercase d, and the unit, meter. Now again, if you would like the entire chart, the entire list of first year physics, scalars and vectors, go to the Study Skills section of the website, look in One-Dimensional Kinematics, and look for the entire list of scalars and vectors. But for now, this is just to help you get started. Now what you can do is make this chart and keep it in your binder. And as you learn more scalars and vectors, add them to the chart. Now, why is this chart useful? Because if you keep distance and displacement together and always say them together and always say distance first, distance and displacement, we could call this a scalar-vector pair. And if you always say the scalar first, distance and displacement, you will remember that distance is the scalar and displacement is the vector. This is a memory technique. All right, so time stands alone. There is no corresponding quantity that relates to time. But distance and displacement are a pair. The scalar, distance, comes first, and the vector, displacement, second. So use this chart and this memory trick if you find it helpful. Now we'd like a definition for distance and a definition for displacement. So, 1, 2, 3, poof, there they are. The definition of distance and the definition of displacement. Distance is the length of the actual path followed by an object. Displacement, on the other hand, is the change in an object's position directly from start to end. All right, now let's look at some simple, straightforward examples of how distance and displacement are different and why you might want to have two different measures of length, one a scalar and one a vector. All right, here's a nice, simple, illustrative example. Li Ju is a young lady who lives in New York City. All right, she's in New York City. That's where she would start. And she would like to visit Washington, D.C. All right, so we'll put Washington, D.C. down south here. All right, Washington, D.C. is where she will end. So let's say, for example, that Li Ju has two options. She can either drive from New York City to Washington, D.C. and visit a lot of her friends and relatives along the way and do some fun things, or she can fly straight from New York City to Washington, D.C. All right, if she drives, this is her plan. She plans to drive 70 kilometers to New Jersey, and she's going to visit her aunt. Then she's going to drive 100 kilometers into Pennsylvania, and she's going to visit her cousin. Next, she's going to drive 60 kilometers. She's going to stop in Delaware to see a friend of hers. She's going to then drive to Western Maryland, all right, another 70 kilometers to Western Maryland and do some hiking. And finally, she'll drive the last 100 kilometers down to Washington, D.C. So she's got a 70-kilometer drive here, a 100-kilometer drive here, not to scale. She's got a 60-kilometer drive here, another 70, and finally 100 kilometers here. So the total distance, the exact path that she will take if she follows this path, if she drives and stops in all the places she wants to stop, is going to be 400 kilometers. You simply, to find the total distance, you simply add up each of the individual distances. So we've got 70 plus 100, 70 kilometers plus 100 kilometers plus 60 kilometers plus 70 kilometers plus 100 kilometers. The total distance that Li Ju will cover if she drives and follows this path is 100, 200, 330, 400 kilometers. So the distance that she will cover will be 400 kilometers. Now, what is the displacement from here to there? To figure out her displacement, you draw a line straight. Let's make sure it's straight. Let's use a meter stick and make sure that it's straight. All right, straight from start to end. We could make that a little bit darker. So here's the displacement, straight from start to end. Now, if she decided to fly from New York City to Washington, D.C. by airplane instead of driving, then we would be looking at the displacement. And that would be, in this case, 325 kilometers. So, this is one situation where the distance, where we would want to know, Li Ju would want to know the distance in one set of circumstances, and for another possible situation, she would want to know the displacement, straight from start to end. So this is our first. So, just to summarize, for Li Ju, if she drives and goes to all those different places, the magnitude of the distance she would cover would be 400 kilometers. if she flies, then the magnitude of her displacement would be 325 kilometers. Remember, in this video, we are not going into detail about the direction. We will go into detail about the direction of displacement vectors in a lot of detail in other videos. All right, now how about another example, another nice simple example of when distance is appropriate and when displacement is appropriate. We have a young lady named Katie, and she is on the track team, and she would like to run 5 kilometers to practice one afternoon, but her mom is very concerned that she doesn't get lost. So her mom says to her, Katie, I want you to map out your run very carefully because I want you to start and end right on the corner in front of our house. They live in a corner house. All right, so here we go. All right, Katie, we'll put Katie's house right here. So Katie's house, this is where Katie is going to start. Now, she's going to run from the corner by her house. She's going to run first 400 meters north. 400 meters north. Then she's going to run 1,200 meters east. 1,200 meters east. Remember, she wants a total of 5K, 5 kilometers. So she needs to run a total of how many meters? That's right, 5,000 meters. So next, she heads north again, and she runs 600 meters north. She turns west and runs 1,500 meters west. She heads south down another street in her neighborhood, and that would be 600 plus 400, that would be 1,000 meters back to her block, south. And what's left here? How many meters does she have to run to get right back home so that start and end are in the same exact spot? Well, if that's 1,200 and that's 1,500, how many meters is she running from here to here? You're right. That would be 300 meters east again. So let's see what happened here. Let's figure out the distance that she covered. You add up all the distances, all the little runs, add them all up and get the distance, the total distance that she covered. We don't care what direction she's going. Distance is a scalar. We don't care about the direction. Just add them all up. So she went 400 meters plus 1,200 meters plus 600 meters plus 1,500 meters plus 1,000 meters plus 300 meters. What was the distance that she covered? We've got 4, 6, 12, 17, 20, 0, carry the 2, 3, 4, 5. She ran 5,000 meters that afternoon. So the distance, the magnitude of the distance that she covered was 5,000 meters. Now, what about the displacement? From start to end, she didn't go anywhere. If she starts and ends in the same exact spot, like she did here, then what is her displacement? What is the magnitude of her displacement? What is her change in position directly from start to end? That's right. Her displacement in this case is 0. So her displacement, the magnitude of her displacement is 0, we'll just say 0.0 meters. Okay, so she obeyed her mother. She was a good girl, and she ended up right back home. She did not get lost. Okay, so she ran her 5K, her 5,000 meters, and she also satisfied her mother's request that she not get lost. Again, a simple